Right. Right, I'll probably start now. Hello everyone, thanks for coming. And thanks for everyone online as well. I'm a research associate in the Department of Materials in Imperial College London. My topic today is understanding micromechanics of nuclear structural materials in light water reactors. So this work is supported by MIDAS, which is an EPRC fund, and it's a fund got amongst lots of universities, including Imperial College, Oxford, Manchester, led by Manchester, and also UKEA was supporting us back then. So in this work, I'm gonna mainly give you a brief introduction of what I did inside this grant, including the Hadron modeling and hydride modeling in Zircaloy. So gonna be a bit educational, I would say, rather than going into too much of the details. So let's start it here. Oh, just before we start, I'll give a brief introduction of myself. So I was born in China, in southern China, in a city called Hangzhou, where I grew up, and then in my year 17, I thought like, think it's a board in the south, let's go northern. And then I go to the northern part of China, which is called a city called Dalian, where I spent my bachelor's and also the first 2 years of my PhD. And I spent over 6 years here and feeling a bit normal. So like I want to find something interesting. And I thought probably I should go abroad. And then I got the chance and then transferred to another city called Nashville, which is in the middle of US. And I spent 2 years there learning from the people around me. Actually, because I was in a quite different environment. So I feel a bit lonely and also not quite accustomed to the English environment. And by interacting with the people around me, I feel more confident, and also they give me a lot of advice on how I should do the research properly with respect within my PhD. And also I get met my wife there, and at the end of the PhD, we married and then moved to another city, which is now London. So at that time, I basically got the PhD, I got married, and got a postdoc offer in Imperial College London. I feel so great. I think everything went so well. And I think this is gonna be a fantastic life here in London. But later on, I found out an article which is on Nature, basically saying that postdocs are glorified PhDs. And that's sort of like a statement that put me back to reality. And then the COVID happened, definitely. My ambition dropped a little bit, but soon later on recovered. And most of the time I spent just in front of a desk, trying to do the research properly. And the following work gonna be focusing on the nuclear energy. So if you started to think about nuclear energy, what would be your image in your mind? Probably starting with some nuclear atom splitting with respect to the neutron, and then releasing the neutrons to splitting more uranium atoms so that it will induce a chain reaction. Or maybe something related to the big power plant, nuclear power plant, where you can see overall in the mass landscape. Or if you go into the engineering side, you're probably gonna be more interested in what's inside the nuclear reactor. So like how they pump up the steam and then turns the turbine and then generate the electricity afterwards. Or maybe if you go into the news, you would see the disaster of Fukushima in 2011. And these are all going to be the general information of nuclear energy. But although there's an accident happening, which is actually at 2011 here, where you can see that the nuclear energy is dropping a little bit, but then later on it went back up, and now it's already overcome the previous nuclear energy generation. And also, it's sort of like a worldwide acknowledgement that the nuclear energy is necessary for us to fully transition into a green energy environment. In the UK, UK actually becomes the first major economy to pass a law called net zero emission. And it's targeting the UK to bring all greenhouse gas emission to net zero by 2015. That's quite a strong statement, I would say. And regarding the later on rationale analysis with respect to the suitability of we actually going to net zero and the rationality of doing this properly, lots of reports have been done to investigate this. And there's a report which is called Absolute Zero here by UK Fires. The Fires report point out that if we eliminating other energy sources, just using the green energy, and then we assume an incremental increase of the technology, we are not going to get what we want, which is the total energy supply in the 2050. And we need some energy innovation in the end. But the energy innovation, when it's being constructed, it needs years to deploy them. The minimum time to actually realize a new energy technology takes about 20 years. And then you have to follow in the marketing, the commercialization, and then it starts to grow some of the energy and then go into the higher amount. So it has to acknowledge the fact that nowadays we need new technology to being invented, but there's not many existing and we need more. That's the first point. The second point is that the nuclear energy will still be a major sustainable energy source that we can doing this transition to net zero smoothly. And Britain has already proposed 8 sites, which is a designated nuclear sites. Apart from there, there's a new nuclear energy challenge, which is called small modular reactors, where 6 companies are selected to getting their technology advancement by mid-2030s. So these are the small modular reactors that is proposed by Rolls-Royce, which is a schematic figure. But basically, the small modular reactors are aiming to supply the additional needs in the rural areas or the other additional areas. And then it needs to be constructed easier than the previous ones. And it needs to be modularized in each of the components that they want to assemble. So a lot of the new designs of the technology has to be proposed so that we can actually realize this technique in a sooner fashion. So just going to the details of my research here. My research is focusing on zirconium, that is a fuel cladding material, which is one major part of the nuclear energy. And these fuel cladding materials would would be used in the bearing pads, fuses, and cap, and also supporting plates, etc., which is back then a typical can-do reactor. In the reactor conditions, zirconium would react with the hydrogen to be oxidized and then release the hydrogen. And this process is going to be accelerated at higher temperatures. And this is basically what happened in Fukushima, where the coolant water cannot be flowing at that moment. And then the temperature started to rise, and the acceleration of this chemical reaction leads to the accumulation of the hydrogen, and then leads to the burst and explosion in the Fukushima. That's what we want to avoid in the end. So this is a typical delayed hydride cracking, which is another mechanism where this chemical reaction would happen, but it is in a long-term fashion where those hydrides would actually accumulate, especially when there's a worst case scenario stress riser, which is notch inside the cladding tubes. And we want to understand this kind of engineering problems better so that we can avoid the disasters and ensure the structural integrity of the nuclear fuel cladding materials. So going to a bit details, these hydrides, when they are going through these long-term thermo-mechanical cycles, they would experience a reorientation, which is basically dissolve at high temperature and then reprecipitate into other locations and then reoriented to a more to a position that is bad for the material to sustain and also easier to lead them for cracking. And we want to avoid that, especially when there's a fluctuation in the small modular reactors. These kind of phenomena could be easily happening if we cannot sustain the stress and temperature range in a super range. And there's already be existing hydride modelings regarding this kind of problem in a mechanistic sense, which is all at a lower level, where you can see the phase field method can be reasonably capturing well on the experimental observations. And the first principle method gives the explanation of how these crystal structures, what we call hydrides, would form in zirconium matrix. But the disadvantage would be the phase field method. It will takes up a very short time throughout the history, which is basically hours in the real thermomechanical cycles. And also the length scale that they are simulating is about 10 nanometer, which is not really relevant to the industrial scales that we want to understand, and also the microstructural responses at the crystal level. The first principle method, they have lower time and length scales. And back to the actual engineering problems, it has to go through a very long thermomechanical cycles within hours. And also the temperature range could be changing drastically during this long holding, stress holding period, and also temperature holding period. So we are more interested in the microstructural responses of the material, basically relating to the real cladding material, while we focusing on the microstructure, which is just beneath the bulk material strength. And then we can understand the hydride behaviors at that length scale and also at longer time scale. So first we want to understand something before we go into the hydrides, which is the material itself, the Zircaloy material. And we want to input into a worst case scenario where there's already a notch in the sample, and that can raise the stress intensity similar to the case in a cladding material. And we put up a 3-point banding test where there's a predominant crystal structure where the crystal structure C-axis is out of plane. And there's a region of interest just next to the notch, where in this region of interest, we did EBSD and a DIC, where EBSD would give us the crystal orientation information, and the DIC would measure the deformation on the surface of the specimen. In that way, it would enable us to understand the deformation behavior at the crystal level directly, and also at the longer time scale as well, which is a 1 hour holding period. And on the surface of the sample, we'll put on the speckles, where the speckles is about 1 to 2 microns, where we can understand this behavior at this length scale. And you can see that these grains we created specifically to enlarge them so that we can understand the crystal level behavior in a much detailed fashion. And we create a finite element method for the crystal orientations that is taken from EBSD. You can see that this polycrystalline structure is mostly C-axis out of plane, and some of the grains would go into another direction. And we want to understand it, the most of the behavior would take part just next to the notch. And then we applied a crystal plasticity model, which basically you can understand that when the metal deforms, the most of the deformation is absorbed by the plasticity. And when you want to activate the plasticity in the material, it's activated through different crystal slip systems, where these slip planes would activate specific directions of the dislocations that can accommodate the plastic deformation within the material. And the crystal plasticity would be able to describe each of the components in these slip systems to accommodate the plastic deformation in the crystal level. And also we have parameters to understand the behavior of the material strength as well as the rate sensitivity of the material, which is basically during a long stress holding period, you would expect the material to be changing with time, which is rate dependent. Okay, so this is basically the result where you compare the experiments with the simulation. And during this 1 hour holding, you can see that at the beginning of the holding, the plastic deformation increased significantly. And then it stabilized a bit more, but still it continued to increase from, let's say, 20 minutes of the holding period. And the creep strain accumulation is massive compared to the other deformation mechanisms, where basically in the bulk, there has been reported that the plastic strain accumulation and also the rate sensitivity of the material is minimum. But actually, in the real sense, near the notch, we actually have the rate sensitivity, which is significant, higher than the bulk material. So there's existing the heterogeneity of the rate sensitivity in the crystal fashion. And we can quantify this by incorporating the microscale rate sensitivity into the formula of the bulk. And this gives us the local strain rate sensitivity, where at the beginning of the holding, you can see that the rate sensitivity is maximized and then stabilized afterwards, which is consistent with the simulation result. This gives us the potential to quantify the plastic strain accumulation, which is a creep strain accumulation in individual spots, where you can see the plastic deformation is captured relatively well, compared to the deformation. And the mechanism behind it is basically the activation volume and activation energy that is controlling the rate sensitivity at the local spots. And this accumulation of the creep strain could not be ignored because near the notch, a little bit away from the notch 1 and 2 position, where the creep strain accumulation is more than 50%. That means that if you have a notch inside the cladding tube material, it's gonna be creeping much when you're holding the material at a longer time scale. So now we have already understand the material strength and the rate sensitivity at crystal fashion for the Zircaloy. We want to understand the property of the hydrides individually. And thanks to the microscale testing, which is called high resolution DIC done by Rhys Thomas, previously back in the 2021, I think. And then he's able to quantify the deformation of the material, specifically near the notch, near the hydrides. And also you can see the sleeve activated within the hydrides as well. That's what we are particularly interested in, because the hydrides, we usually think it as an elastic material. But in this case, we want to understand how these plastic deformation really occurs within the hydrides. So by applying the same technique, which is crystal plasticity again, we begin to understand the behavior a bit better, where the sleeve actually transfer from the matrix to the hydrides, and then it's going to be transferring out as well to the matrix. So there's a complex interactions between the hydrides and the matrix involving these sleeve activation mechanisms in both matrix and the hydrides. This is only done in room temperature, and it's expected to be more complex when you have the higher temperature involvement. And then compared to the other temperature sensitivity studies from the experiments, we've been able to capturing the material strength of matrix, which is called Zircaloy, and also the hydrides in the material, and also the rate sensitivity of the material as well, which would be able for us to quantify the plasticity accumulation in the hydrides and Zircaloy. Now, later on, we want to bring these two things together, where we have already got the hydride property and the matrix property. We want to model how the hydrides precipitate out in Zircaloy. First, we have to understand the mechanism in the hydrogen, where you can see this mechanism as salt within water, where you have put too much salt into the water, the concentration becomes too high, and then the salt begins to crystallize. And then this is sort of like what we taken from the first principle method, where the atomic scale information, we want to incorporate that into the modeling, where you can use a term called elastic dipole tensor, which you can sort of like seeing it as a stress pinning the hydrogen atoms within its preferential site, which is called a tetrahedral site in the material. This tetrahedral site of the material is pinned by the interactions between the hydrogen atoms and the lattice, which allow us to quantify the interaction energy and also the chemical potentials. So by minimizing the thermo-mechanical potential, we can link the hydrogen concentration with respect to the local deformation stresses and as well as the temperature, so that we have a mechanism that the hydrogen concentration would change within the microstructure with respect to the local temperature, as well as the local stress and strain. And then when we understand the hydrogen concentration, we want to change it to hydrides. But there's a distinct difference between the hydrides at the bulk and the hydrides in the nanoscale. Where in the literatures, the bulk of the hydrides at the relevant temperature that we are simulating is between about 20 to 300 ppm. Whereas the local hydrides, when it is observed in the nanoscale, which is called, which is from a technique called atom probe, where the atom probe tomography would give you the local atomic hydrogen concentration near the hydrides and also inside the hydrides. This would give you the gap between the hydride at the local and the bulk. And then we want to bring them together with respect to the phase transformation, where we integrated intermediate phase, and then we incorporate this volume fraction, a volumetric misfit strain percentagely with respect to the local concentration of the material. And then we can precipitate out the hydrides as well as dispose them in the material. So for understanding the hydride precipitation throughout the long thermo-mechanical cycle, there's going to be experimental understanding so that we can integrate the experiments and the modeling together to understand it a bit more. Where we first hydrogen charge the sample and then put the hydrogen charged sample within a 4-point bend rig, and we apply the thermo-mechanical load onto the sample with the hydrides embedded. We also have a notch at the sample as well, just to give it a worst case scenario, which is relevant to the stress intensity factor that is within the real reactor conditions. There's two samples that we've been simulating previously, and I'm gonna focus on the sample A here, where you can see that we first gonna be focusing on the hydrogen concentration, where without the hydride precipitation, we just see how the hydrogen gonna distribute within the microstructure. In sample A, you can see that on the left-hand side is hydrostatic stress, where basically you can see it as the pinning stress that pins the hydrogen at the local spot. This actually leads to the hydrogen concentration, which is relevant to the hydrostatic stress distribution at the higher spots. And due to the temperature change, which is temperature dropping here, the hydrogen concentration drastically dropping to a certain level, but retained at the green boundaries where these are the highest spot of the hydrogen, which is related to the green interactions, where those green interactions leads to a higher hydrostatic stress at the local green boundaries and the high hydrogen concentration. Now we know that hydrogen concentration could be influenced by the microstructure that we are simulating. Now, during the temperature hold and also the stress holding period, where you can see that the hydrogen would change as well, but this is relevant small compared to the temperature change in the material, because the temperature will basically change the concentration of the material significantly, hydrogen concentration significantly. During the stress holding period, where you can see the hydrostatic stress change a little bit, but the hydrogen concentration changed a bit more compared to its level within the microstructure. This is due to the plastic deformation, which is at the notch that push up the hydrogen into the material a bit more when the stress is holding. And if you look at the cyclic hydrogen redistribution, where we implement these 3 cycles within this hydride sample, the hydrogen would be driven up cyclically, which is first driven by the plastic strain, and then go into the hydrostatic stress would be higher cyclically as well. And these two drive up the interaction energy, and then accordingly, the hydrogen concentration would be higher and higher cyclically near those grain boundaries. And this is just to point out the strain rate sensitivity, which has an important factor here, where if we incorporate the correct activation volume, which is rate sensitive, it's going to give you the accurate responses on the hydrostatic stress, as well as the redistribution of the hydrogen concentration next to the grain boundaries. Whereas if it is a rate insensitive fashion, the hydrogen distribution is much more homogeneous, where there's little redistribution near the grain boundaries. And now we're going to look at the hydride precipitation, where you can see that these hydrogen redistribution near the grain boundaries would actually induce a higher hydrogen concentration in the microstructure in specific spots. And those specific spots would turn into hydrides, and those hydride precipitation would change the local mechanical responses and then precipitate a bit more into during the temperature dropping period. And in the following cycle, if we increase the temperature, the hydrides start to dissolve, but it's not dissolved fully if we actually go into the subsequent cycles, because there's going to be retaining dislocations within the microstructure, which will increase the hydride precipitation cyclically. Where you can see that cycle by cycle, when the hydride precipitated out, it starts to accumulate, but it stabilizes a bit more in the third cycle compared to the increase of the hydrides from the first to the second cycle. And then there's another sensitivity study which is interesting, where we're dropping down the critical limit of the hydrogen concentration limit for it to form the hydrides. It basically means that we are incorporating more nucleation sites for the hydrides to accumulate. And then the hydrides would form following the stress intensity distributions, which are going to form these bands of hydrides, and consistent with the previous studies where there's equiaxed grains, basically the means more nucleation sites in the material, and more hydrides would form in this fashion. So in conclusion, integrating with the microscale experiments, the micromechanics would actually be very valuable to understanding what is actually happening by incorporating both experiments and modeling in the same location. And then the historical change and also the heterogeneous distributions of the material would be predicted relatively well, and to understand its dominant mechanism in the material. Grain level properties could be validated to set the base for different crystal structures. And we have to emphasize here that grain level microstructure is the closest subscale linked to the failure mechanism in the bulk. So by proper upscaling of this microscale behavior, the crystal plasticity model would be beneficial to understand the long-term behavior of Zircaloy, and then it will be providing guidance for the microstructural design, especially in the new structural design within the small modular reactors, or in the new nuclear design in the nucleation sites. In the later stage, we have already been working on the irradiation effect of the material, where the irradiation would interact with the previous hydrogen and also temperature and hydrides evolution, as well as local stresses, so that this would bring up to a whole new level of understanding. And then this is going to be increase our confidence in the modeling, so that we can provide more mechanistic understandings behind the industrial applications. So just a bit more context here, where right now I have fortunately taking a position now in Leicester, where I'll start to 1st of February next month to be a lecturer in Leicester. So please feel free to contact me so that if you have any ideas and want to collaborate in any sense. And I'm gonna move to the north again here, which is previously starting from Hangzhou to Dalian, but now London to Leicester again. Who knows what will happen next, but it's gonna be an interesting journey. Okay, thanks very much for the kind support for all my colleagues in Imperial, Manchester, Oxford, King's College, UKA, etc. Thank my parents, partner, and friends for their support. These kind of works cannot be done without their support along the way. And also, I'm open to any questions, ideas, and suggestions. And please email to me if you have any. Right. Thank you very much for your attention. Thank you. Okay.
So you're saying so the notch is the worst case situation.
Yeah.
I suppose in sort of normal reactor operation, those stresses are going to be coming from the oxide layer growth. Do you think that that will also cause significant plastic deformation accumulation in a similar sort of way to the notch, or to what extent do you think that might be less just with the oxide layer formation without any sort of notch?
Right. Yeah, that's a good question. Yeah, I'm not an expert in oxidation in Zircaloy, but I would assume that the oxidation, when the oxidation happens in Zircaloy on the surface, it's gonna accumulate plasticity, I would say, but not in an engineering scale. I would say probably in like a local scale, induce the dislocation accumulation between the interface of Zircaloy and Zircaloy hydride. And then it's gonna increase the potential for the cracking to form in the interface of these two, and also inside the oxidation layer as well. And the oxidation layer, of course, is gonna be the dominant factor for the cracking to happen in the first sense, and then it's gonna propagate to the interface of the Zircaloy and the Zircaloy hydrides. And that's gonna be basically the mechanism behind those like imaginary notch type structure that we perform, I guess.
Yeah. Do you think then that sort of the metal to some extent can be relieving some of the stresses within the oxide, potentially delaying the cracking in the oxide?
You mean the plastic deformation?
Yeah.
That's one possibility, yeah, definitely.
Okay.
Yeah. But the interaction with them would be complicated in that sense. Yeah, I'm not saying that this going to happen to delay, but potentially in another sense could be detrimental as well. Yeah.
Thanks.
Yeah, thank you. Any question from online? No? Not really, okay. Yeah, thank you. Thank you. Right. Thank you very much.